Good morning, everyone. Thank you for joining us. Let me introduce Mr. David. No, yes. David is a principal software engineer at Splunk, working on their data stream processing engine, and also as a contributor for the Apache Pulsar project. Prior to Splunk, he was the director of solution architecture at Streamlio, where he has responsible for development of the best practices and solutions for the professional service team with a focus on streaming technologies, including Pulsar, Kafka, NiFi, and Storm. He's the author of Pulsar in Action and holds a master's degree in computer science from Kent State University. Thank you, Mr. David, to share your knowledge with us today. So you can go, please.
Thank you. Thank you very much. Thank you for that wonderful introduction. I know I didn't share my pronunciation of my name with you. It's David Kjerrumgaard. So don't let the large name intimidate you. Thank you for that wonderful introduction. Hopefully most of you who joined in on this session got a chance to see the keynote this morning by Karthik Ramasamy, who also happens to be my boss. He gave a great introduction on Apache Pulsar and why we chose to use it at Splunk for the core messaging platform within our data stream processing engine to replace Apache Kafka that had previously been in place for that. Today's session will be on Pulsar Functions, which is a lightweight computing framework built on top of Apache Pulsar, and we'll do a deep dive into some of the technology involved. So just to give an overview of the agenda for today, I'll start with a brief introduction to what Pulsar Functions are, what the programming model is, and what they hope to achieve. And then we'll do a deep dive into the internals of the Pulsar Functions itself, the life cycle, if you will, of a submission of a function, how it gets scheduled onto the individual workers to get executed, and then the execution workflow itself. And then finish off with some Java-specific concepts and an overview of current and future work and improvements into the framework as it's an ongoing and ever-changing ecosystem that's rapidly changing. So let's first start with a brief introduction to Pulsar Functions. So what are they? It was the concept of bringing serverless concepts to the streaming world. So those of you who are familiar with what they call serverless computing, it's basically where you create a simple function, a very, very light processing function definition, and apply it to a data stream processing element. AWS Lambdas is a perfect example of that, where you basically provide the code itself, and the infrastructure and how it gets executed is hidden from the user. You don't really need to know how the underlying mechanism works, where it's deployed, what instance it's running on. It allows the developer to focus on the processing logic itself. And so we thought that was a very popular feature. It's a natural fit to the stream processing world, so we decided to create Pulsar Functions. Within there, the abstract view is you have messages coming into a Pulsar topic, for example, messages coming in. The Pulsar function is, again, the code that gets executed, and you can output messages or not messages to one or more output topics as well. So a function has one input, one output on that. The emphasis of the API was to make it simplistic, right? You see there on the right-hand side, that's basically the hello world version of a Pulsar function. It's very, very simple, a few lines of code, very simple, first-year computer science student can understand how to do it, be very productive very quickly with that. They don't need to learn a complex stream processing framework such as Spark or Flink or Hadoop or other old messaging technologies. You basically just write the code and it executes the code on that. And it's what we found is it's a great for 90% of the use cases that you apply to streams. When you have data coming in, you want to perform basic simple functions, stateless functions such as filtering. Does this element have, is this tweet around a particular keyword I'm looking for or not? And if it does, and you want to route it to a specific topic for further evaluation, and then maybe along the way you want to do some enrichment, maybe do some sentiment analysis on that. And all that can be done with a very, very simple logic, type of code Pulsar Functions provide. So it's really a very simplistic framework that we built on top to make it useful to the stream processing world. So within these Pulsar Functions, so you define this code, you go ahead and you're going to deploy it. And the first thing you need to know is that it's a multiple flexible execution environments, right? So for those of you that caught the talk this morning about Pulsar, in general, you basically, or I can review for those who don't, there is the concept of different layers within the processing framework itself. So the brokers here on the Right-hand side at the bottom represent the message brokers. They can take messages in, they publish messages out, they advertise the topics for consumers and users. Underneath that, but not on the slide, is the bookkeeper layer where the messages get stored. And that's a separate distributed layer. But then we've also added the Pulsar functions themselves are these green boxes in the middle called the workers. And they can reside, and their primary function is to allocate and make sure that these functions that you submit can get executed and processed and run. And so there are different types of deployment workers that are allowed within Pulsar functions. You can have them execute as individual threads running in the workers themselves. You can have them running as separate processes along inside those same nodes. So in those gray boxes, they can run as a process inside of there. And then also third, we also support natively a Kubernetes. So they would get launched and run as independent pods and get allocated across your resource pool in a Kubernetes environment. And the top layer indicates those different instances, right? There's function word count 1, function word count 2, transform, etc. And they all just exist within the Pulsar ecosystem, and the workers are responsible for creating those. The note here about the CRUD-based REST API. So we automatically provide tools and an API that allows you to obviously create them, remove them, update them, and delete the functions as well. So you can very simply, I want to create a function, I want to delete the function for a while, I want to update it, basic things, because code evolves over time, you want to change it. So those are the types of APIs and mechanisms you have. So now that we've talked about at a high level what Pulsar functions are, let's get into some of the internals of this. And so the first thing is the submission workflow, right? So let's say you've decided you've written your little hello world there one, that you've taken that simple example and you want to, you want to get started, you want to deploy it. So what you can do is you can submit it to any one of those green workers we saw on the previous slide. It doesn't really matter. It's agnostic. There's no central point of failure. There's no one way to get in, one way to get out. Any one of those workers will accept the submission of a function. But when you submit it, you have to supply some basic configuration, right? You can't just say, here's my code, and go run it. It allows you to, you have to specify things like the tenant, namespace, and name. So within Pulsar, we have a different hierarchy of structure where tenants are like an operational unit, a department unit. It allows you to apply security credentials. Certain data sets are restricted within a tenant. And then similarly, you can deploy, if you're authorized, you can deploy processing on those units using your functions within that tenant. Next to that are namespaces, which are sort of a logical collection of topics or functions that you want to sort of treat as the same. Let's say you have a cybersecurity team within your department that it's responsible for, has elevated privileges. You want to monitor certain data streams that other ones may not have. A namespace is a good logical grouping for that. And then lastly, the name of the function itself. So you have to uniquely identify those three elements together, uniquely identify a Pulsar function. Additionally, you have to specify obviously the input topics you want to consume from and the output topics you want to write to. And then other things like the class name itself, your processing guarantees. Again, you're allowed to do at least once, at most once, exactly once sort of processing, so that how it will handle failures. If it tries to process a message and fails, we'll retry, we'll quit, things of that nature. And there's also here on the right-hand side, there's a map that allows you to configure user configuration properties as well. It's sort of a catch-all for you to have within your code. For example, if you want to have a uniquely defined configurable dynamic properties, such as, again, if we're doing filtering by keyword, for example, then you can have a map within that user config called the keyword to filter on, and you can change that property when you do an update. So instead of filtering on, this keyword, you can change it to that one and you redeploy it, and it's just a configuration change. Other settings like the degree of parallelism you want to have of these functions. You can obviously have more than one of them running in parallel. Again, if they're stateless functions and you want to just scale up and do the data quickly, you can have 5, 10, 20 instances running, whatever you need to do. The other thing that you need to, and this can all be configured as either if you're using the REST API, this all can be configured inside a YAML file or a JSON file. We support either one. And then along with this configuration, obviously you have to support the function code itself, right? That would be a jar file, the Python file, the zip file that includes not only the source code, but any dependent libraries as well. So if you wanted to do something like a machine learning function that does some sentiment analysis, for example, you can upload your Python files and all the different libraries and models associated with that and put it in one bundle, and that has to be deployed as well. That's what gets submitted to a Pulsar function. So once you've bundled all this up and you've configured it, next thing you do is then you submit it. The first thing it does is do the authorization check. So it goes through these steps on the left-hand side one by one. It says, okay, who are you? What tenant are you deploying to? Are you allowed to deploy it here, right? We don't want to have somebody deploying a function that exposes sensitive data in a topic that you're not allowed to access. So first thing we do is obviously make sure that you're allowed to do it. Once that authorization check is passed, next thing we do is look at the function configuration you just provided and do some validation, right? So we look for missing parameters. Did you not specify, the number of parallel instances? Did you not specify, different secrets configuration, things of that nature? And then we can also validate those parameters themselves. Was your number of instances not since it's freeform, was it an integer, or did you give us text instead? Things of that nature, validate those sort of things. Assuming all of those configurations are then valid, we also then check next as we go look at the class name and make sure that class is available at the runtime in the library. Can we load this class? Is the library available? Did they deploy it properly? And if all of those things pass, we have a valid function instance, and that all that code is copied, the library itself is copied to that storage layer called Apache Bookkeeper there at the bottom. So it's a distributed store. So it's always available. So all the workers, all the brokers, everybody has access to this Pulsar function at that point. You deployed it, it's valid, it's good. So next is the function metadata manager. So once that, it serves as a system of record for all these functions that get deployed, right? So again, it stores them all as a map of the fully qualified function name. Again, that's the tenant namespace and function name itself. And then the function metadata that we already validated and approved is good, right? It's backed by a single metadata topic. So it's one continuous topic, and there's one function that reads it and then looks for changes and updates in that stream. And based on those streams, decides if we're going to reschedule those things or not. So all it does is it contains a single event, a single topic of all these different functions that get deployed. So when you're doing, it's basically serves as a state machine, right? Every one of those events in that metadata topic represent a function deployment, a change in the configuration, a change of different of that particular function or multiple functions as well. So just before you do a create, update, or delete, you make a copy of the current state. So we can always roll back if something goes bad. So again, in this case, we have version 2. We have the same function foo. And previously it was running and all the workers was version 2 of it. So first thing we do is make a copy of that. Next is we merge those updates of the submission, right? So let's say again, the keyword, the function filter example that I gave earlier, right? You wanted to change the keyword you filter on, everything else stays the same. The merge would result in just updating that user configuration to be the next keyword that you wanted to filter on instead. Assuming all that passes and everything's validated, then you say, okay, this is a good version or a good configuration. You increment the version to update it, uniquely identified. Now we're moving to version number 3 on that, and you write that data to the metadata topic, right? So now it's a good blessed version. It goes into the audit log, it goes into the history as a valid function, right? So it's sitting there, but it still has to be deployed. All we've done this far is create an update to the table, changed some configuration tables, but now it has to be read and verified and updated in all the different instances, right? There's still all the functions that were running before are still running version number 2. Version number 3 has been published at this point, but not deployed. If there is no conflict, then the tailorer will update the version of all these different versions to 3. So you see in this slide here on the rightmost side that the function details that are now deploying went to version number 3. So what can happen? Let's say there's conflicts occur. Let's say there's 2 different people trying to update the same function at the same time. How do we handle these types of conflict resolution? How do we handle these types of issues, right? So people can do concurrent updates to the same function and both submit them at the same time. Well, in this scenario, we decided to do first writer wins. First one in there that updates the version, gets validated, and grabs that version number 3 is the true version number 3. All other ones are rejected. So if you do it simultaneously, the first one in will get that version update. The second one will say, no, somebody else is updating this function. You can try again later. The advantages of this approach are that you, again, as I mentioned earlier, you can submit these changes to any worker. So that allows you to, and they synchronize on that metadata topic in a central location. So it's a consensus location with a single writer, single winner scenario. So this allows the validation and the load to scale linearly, because if you have thousands, tens of thousands, hundreds of thousands of topics being updated, you can't have any sort of bottleneck in your system. And this allows you to do that very, very easily by having a single location, a single topic at a time. Also, in the event of a failure, complete failure, it forms a deterministic state machine, because we have all those different versions of the update of the functions from version 1, 2, and 3, and all you have to do to get back to the original, to the current state, is to read that from beginning to end, and you take the last one, and that's where you are. So you never lose track of where you are at any point in time. And basically, as this last bullet point mentioned, it allows the metadata topic to serve as an audit log, and the most recent version is always the correct one. Some of the downfalls to this approach, or some of the issues we have to deal with, are in metadata topic growth. That can be, again, if you're doing tens of thousands of functions, that topic can get quite large, and we can do something called topic compaction, which basically eliminates the older versions of these functions. Again, for example, so in a topic compaction scenario, if for that function foo, you would go back and you would delete versions 1 and 2 in that scenario and only keep the latest one. But again, that's a very, it's a non-trivial work. There's a lot of data. You have to scan all the records multiple times. It's very processing intense, and it's a non-trivial operation. Another downside is the worker start time on this. So again, you start up a worker, it has to read that metadata topic from beginning to end. And if it's a very large topic, that takes a lot of time to achieve the proper state. So, but all workers will know everything. All the workers access the same topic. They all have the same consensus on what the state is of the functions. All the functions running in Pulsar land are running off the exact same config. You don't have some function workers running an older version and some a new version. All the workers will be driven off the exact same one. So this is kind of the upside of that as well. So that covers submission. You've created the function, you've written the code, you've bundled it up with all your dependencies, you wrote your configuration, you've deployed it, it got rid of that metadata topic. Now we have to schedule it, right? So there's a scheduler interface. What scheduling basically means in this context, what I'm referring to is identifying a place for the function to run. Again, you have different options. Is it going to run as a thread? Is it going to run as a process? Is it going to run as a Kubernetes pod? You still need to find places within your infrastructure on your nodes that has sufficient resources for this function instance to run, right? You can't just throw it out randomly to one or the other. The scheduling is what sort of handles these operations, right? So again, the scheduling occurs whenever you have an unresponsive or dead workers, for example. It also modifies instances, right? So you submit a function, it was running as a thread for a while, the thread died. That constitutes a worker change, and then it will get rescheduled, right? It'll say, hey, this guy died somewhere, let's put it somewhere else. Also, this gets triggered when you add new workers to your pool, right? So by default, you have, let's say you start with 3 nodes, you have 3 workers, and you scale up dynamically or manually, and you add some additional workers. Now it'll say, okay, let's do some rescheduling, maybe distribute the load a little more evenly. It can also occur periodically. You can schedule your scheduler to run every 20 minutes to scan the environment, rebalance, reshuffle your processing load across all your different nodes. And then it could also happen if you have a leadership change. So again, we'll look at the next slide, but basically there's one worker. Remember, we had 3 different workers in the original slide on each node. One of those is responsible for scheduling. You cannot have multiple people trying to do the same scheduling. You have multiple instances of these functions running that you didn't want to have. So one of them has to be in charge of, hey, I look at all the functions that were submitted. I'm going to go ahead and be responsible for making sure that these workers get scheduled these functions get scheduled as needed. He's the guy. How this has occurred is through what we call coordination topic. And the coordination topic simply leverages a unique mechanism within Pulsar. Again, we have called the failover subscription. So if you saw the presentation this morning Karthik gave. He basically talked about the different subscription types that are available in Pulsar. And one of those is there's an exclusive type, which means one worker can have it. And then a corollary to that is that's the failover subscription. So then if you have multiple workers try to get a subscription to one topic, only one of those will win. And if that one ever dies, the next one in line who tried to get in will fail over and they'll take over automatically. So it allows you to simulate leader election using an existing mechanism that exists within Pulsar. And we just use the coordination topic to achieve that. But basically, what we're trying to do is have one worker be responsible for the scheduling of all the different function instances. Now, what the worker in charge, whoever wins, the leader that gets elected, writes data to the assignment topic, right? So he looks at the submissions that comes in, and he decides where it's going to go, and he writes these assignments out to what's called the assignment topic. Again, it's a Pulsar feature. We use it for free. We just say, hey, here's all the different assignments, and all the different workers can now read from that assignment topic and look for elements that were assigned to them, right? So in this scenario, let's just say worker 2 was the leader, as the previous slide showed. He would publish a bunch of messages to the assignment topic, and he could say, worker 1, you get these 5 functions. Worker 3, you get these 2. And worker number 2 gets the other 2. Those would get written to the assignment topic, and each one would read it and say, okay, I'm running an instance of this worker. I'm going to go ahead and spin one up, right? And so on. And worker 1 would get it, worker 2 would get it, and so on and so forth. So what do these messages within the assignment topic look like, right? It's basically, there's an instance which has the function metadata. Again, everything is defined in a protobuf underneath because it's a very lightweight, compact messaging transfer protocol. It's also always guaranteed to be backwards compatible. So if you ever switch versions later on, the messages will still be, they won't be corrupt, they'll still be readable. And the first one is a function metadata. Again, all the different configurations, input output topics, the name, the parallelism, et cetera, associated with that. And then a unique instance ID of that function. So if you have, again, 5 parallel instances, each one would have instance 1, 2, 3, 4, and 5, or 0, 1, 2, 3, 4. And then an assignment is the scheduler looks at, says, okay, for this instance, which is again the metadata and the worker, this worker ID is one of those 3 workers 1, 2, or 3 we showed in the previous slide, right? It's one of these guys. Who gets it? Who's going to be responsible for spawning an instance of this function? And that's it. So that's all the different metadata there, and that's how it scatters and distributes these functions that have to be running across all the different workers on their serverless compute framework that's inside of Pulsar. So once it's been scheduled, and it's in that assignment topic and a worker gets it, let's look at what happens next. And that's called the execution workflow, right? So again, now I'm worker, one of the individual workers. We're drilling down into the worker itself here in this slide. And let's just say this is worker 1. It's going to read the assignment and say, hey, I'm the worker ID in this assignment topic. This one's mine. So I'm going to read this message out. I see that I have this function configuration. And now I have to figure out how to start an instance of this function running so that it can do all the fun, wonderful processing, filtering, transformation, sentiment analysis, whatever I really want it to do underneath the covers. It'll read that, and each worker has what's called a runtime manager that allows it to spawn off instances of these individual functions, right? And the runtime manager depends on the programming language that the function is deployed in. So again, currently Java is one that we support. Python is another one. Go is another one, right? So everyone will have a different runtime manager based on the execution environment because it has to provide, that runtime library, the interpreter, the JVM, the Python library, et cetera, that's required to do that within there. So those are different runtime managers that work. It then has different spawners. Each spawner is responsible for actually running the function themselves, right? And there's a spawner for each deployment type. Remember, you could run as a thread, you could run as a process, you can run as a Kubernetes pod. So a spawner, there's a thread spawner, there's a process spawner, and there's a corresponding Kubernetes spawner. And each one knows how to take the metadata that was given in that assignment and spin up a corresponding either thread, function, or Kubernetes pod with that. Additionally, it also maintains this open gRPC communication channel, so it can always do updates and monitor the state and do updates on that and make sure that it's alive and running. But basically, it's responsible for running the instance, right? And if anybody has done some development with Pulsar Functions, one of the useful tools that comes with testing it is something called a local runner. So it allows you to run and test your functions locally on your desktop within your IDE itself before you stand up a whole Pulsar cluster to deploy it and run. It sort of allows you to short circuit that whole deployment to test cycle. And the local runners is nothing more than it implements that same process, right? There's a spawner, Java runtime spawner, Python runtime spawner that spins it up for you, directly uses that automatically, right? So it's a simple interface that allows you to create different execution environments, right? It's the runtime factory I talked about earlier is, hey, do I want to spin up a new thread? Am I starting a new process? Am I creating a container in this particular scenario? It's, Kubernetes container that has these different, if I want to specify a unique instance, for example. So if I'm deploying a Pulsar function that uses TensorFlow or some other, needs a third-party specialized Docker container, I can also automatically load that up and use that within this framework. It doesn't matter. It's agnostic to that. You give it the Docker image, it can spin it up and deploy it as well. And basically creates those instances that are running, right? So now let's talk about the Java instance themselves, because it's the most mature of all the Pulsar functions. I know we support several, including Python and Go and the other ones I mentioned. But Java, since Pulsar is written in Java, most of the leading work is done in the Java instances. Let's talk a little bit about those before we wrap up on final work. A Java instance is just a logical abstract around a source, an abstract source, a function, and a sink. So it abstracts the reading from the input away and abstracts away the writing to the output topic. Really, from your perspective, it's just provided for you automatically. Again, if you're a function, the messages just magically appear and you get invoked. And when you write an output message, they automatically just get written to a sink, right? And so by default, it's written to obviously first work with Pulsar, right? It's consumed from an upstream topic and right to a downstream topic, right? And that's it. So the natural state or the first state is Pulsar function back to Pulsar. But what if you want to have a non-Pulsar source? What if you want to use something else besides, Pulsar topic as the input to this? Well, that becomes what we call Pulsar IO. In a particular Pulsar IO source in this scenario, because you're reading from a non-Pulsar source, it allows you to read anything from an external system. So let's say you have something like, want to read from S3 or a Kinesis Firehose, and you want to read those events and then process them. That's the Java instance allows you to have a non-Pulsar source. It uses the identity function, which is just a placeholder for your function, and then write out the data to the topic. So you basically can simulate a Pulsar function with this identity function in Pulsar IO and adapt to any other external source. Similarly, you can have a sink is the converse of that, right? You can have data reading from Pulsar and write to a non-Pulsar sink. Again, the identity function is used in this scenario as well. So you can read an input topic, it does a pass through, and then you can write the data to a non-Pulsar sink, such as a database or other, Kinesis Firehose on the output. Anything you really want to write to as well, that's Pulsar IO. So let's wrap up a little bit about current and future work, some of the things that we're working on. So the first is dynamic runtime selection, right? So I mentioned earlier multiple times that your runtime managers, you can spawn different types, right? You can run them as threads, you can run them as processes, you can run them as Kubernetes. Currently, you make that decision once, and it's universal for all your functions. And in some cases, you may not want to have that sort of blank assignment, right? You might have more granular control whether I want to run these functions as threads, I want to run these other ones as processes, and I want to run these as Kubernetes pods, based on what makes sense for you, right? It allows you to, and also change it dynamically at runtime as well. So you run it as a thread and it starts having resource contention, you can spin it up to a process. And if it becomes bigger than that, you can do run it as a Kubernetes pod as well. That's something that's currently in work that allows you to dynamically specify that as your function configuration. So again, when you deploy it, along with all those other configurations, you could specify, hey, run this as a thread, hey, run this as a process. Other thing we're going to do is on that metadata topic compaction as well. We've talked about a little bit why that was inefficient previously on that, and how there's just having a very long, unwieldy metadata topic is bad for performance for a multitude of reasons, and how that was a very difficult process to solve. We're going to work on working on compaction of that. Again, compaction just means deleting the older versions and keeping the most recent copy of that particular version of function details, so that it's all, because that data is no longer relevant or recent. You just purge the topic of all those different records, and it makes it much easier to work with. So that's another area of future work. One that I'm particularly interested in and working on is this concept called function mesh. So as you may have logically thought, again, you have a basic programming model and functions where you have data coming in and it writes it back out. Well, you could obviously see where the output of one function could be useful as the input topic for another function, and so on. You could basically chain these ones together and create what's called a mesh or a function mesh, and dynamically specify that more dynamically. So you could say function 1 feeds function 2, function 3, and all that underneath the covers, function names, and the input-output configuration will be done for you automatically. And allows you to have a simple workflow API where you just write the code and you link them together very simply, and all that underneath the covers is handled for you automatically as well. And then lastly, one of the things that we're currently using at Splunk for large data collection team that I'm working on is what's called the batch source. So a lot of times, again, the function, if you notice with the programming model for Pulsar Functions, it was triggered on when an event comes in, right? So you receive an event that triggers the processing of the function runs and then generates output or not. But what if you're trying to collect data from different sources that don't really have that type of scenario where you're publishing a message every time to trigger it? Again, a classic use case would say, let's say you want to scan an S3 bucket periodically to look for new records or new objects, and then parse those out and put that into an input stream to do some processing on it, right? A batch source allows you to do that because you can schedule to run periodically. And then it calls what's called this discover phase, where it says, okay, let's scan the S3 bucket and identify the work I have to do. And then it generates a bunch of tasks and publishes those to an intermediate topic. And then the prepare method gets called for each one of those, and it can process those things in parallel. So it does a lot of different process. It allows you to do it, process a lot of different messages that are not event-based, but more static data sets. And you periodically want to scan them for data and collect the data as well. It's a repeating cycle, periodically scan for an S3 bucket once an hour, et cetera, those types of work. So those are the things we're adding to Pulsar Functions as well. And with that, I think I'm just about done. Thank you for your time, and hopefully there's some questions. You found this useful, and if there's any questions, we'll see what we have.
Thank you, David. I didn't see any question in the QA section. If anyone has one question, could you please post it on QA? Or maybe Nancy, do you have any question?
Oh, okay. I am not that familiar with Pulsar, but I was wondering if this is a messaging system. So it's an analog to something like SNS in if you're using Kubernetes in AWS, or am I completely off base because I don't really understand Pulsar that well?
No, you are correct. It is Pulsar is an enterprise messaging system, so it's similar to. It's along the lineage of JMS messages or IBM message queue. If you go way back to there, more common one is a distributed messaging system that's like Apache Kafka or things of that nature. So you really have, it's a pub sub mechanism. So you publish messages, you have topics, and then you have people who subscribe to those topics to receive the messages.
And you wouldn't be able to import this into AWS like as an outside code. This is for use with Apache and open source like that.
Correct. I mean,
okay.
what you could do is you could host, again, a lot of people who offer Pulsar as a service hosted in messaging space up in AWS. So it's transparent to you. Again, it's like, so it can be like SNS to you transparently. And then you can have, rather than Lambda functions, you could have Pulsar functions. So
okay.
you can do everything within the cloud because it can be a hosted solution in the cloud.
I was thinking that, but thank you. That's all. Those are my only questions.
Oh, great
Thanks.
questions. Thank you for those.
I don't have anything in the Hoover app. So,
Okay.
Ruben, should we wrap up?
Yes, I think we should wrap up. Thanks again, David, for sharing your knowledge about the Pulsar infrastructure and new works.
All right. Thank you very much. Have a great day.
Okay, have a great day.
Bye.
Bye-bye.